So, okay, so once again, we're trying to turn our program, our ability to solve the problem, as simple as that, into an algorithm in such a way that the computer can carry it out, and then the computer would be doing all the job because after all, this kind of 2x2 system we can do by hand. Beyond that, it becomes very hard, and it is possible. It is totally realistic and real that having hundreds or thousands of equations with hundreds or thousands of unknowns. So you got to let a computer do it. I'm not going to lie to you. The algorithm that we're going to develop is not going to be real. So it has flaws that the computer would not be able to overcome. So it's not a truly the way it is done. So if you're interested, you would have to take a course on numerical linear algebra in order to see how it is actually done. In order to, what computers do, the division by zero, numbers too large, too small, too much memory is taken, so all of that we ignore altogether. Okay, so we'll stick with elementary linear algebra. So in that sense, the algebra is elementary. So we are, the computational stuff is left for the future courses that you might take. So once again, so ideally we want to see the identity matrix over there. This is the process once again as we go through these steps, moving rows around, some algebra with rows, as if those rows were vectors, right? So that's totally scalar multiplication of vectors as well as addition of vectors. Okay. At the end, ideally, and that's what happened here, you end up with our coefficient matrix becomes the identity matrix, which is, in generally, a square matrix. Remember, you can multiply matrices of all sizes, but the particular nice matrices are the square matrices, meaning that they have the same number of rows as columns. Okay, and what is so special about it, it is with all entries 0 except ones on the main diagonal. Main diagonal means the one that goes from left to right, from top left to bottom right. And the rest is zeros, so I put big zeros here. Denoted by I or I sub n, if you want to indicate the size. Okay, so that's where we want to end up, but we already know that's not always going to happen, because not all the system of equations produce outcomes of one answer. So whenever you end up with an identity matrix, you have your answer. Well, let me point it out. Well, we did point it out, but the final result of our analysis was the matrix on the right. And what has happened is, as you can see, all the complexity was with the matrix that we started with, a matrix of coefficients. This one, the starting matrix was this, and we, through elementary row operations, we were able to eliminate all the complexity, and then all the complexity ends up here, which happens to be the answer. Okay, however, that's not the only possible outcome, so let's look at another possible outcome following the same procedure. So just for practice as well, so my system is, say, x plus y is equal to 1, 2x plus 1 is equal to 2. Okay, augmented matrix. Which is not a matrix. 1, 1, 1, 2, 2, 2. Okay, so once again, we're trying to somehow arrive to, if possible, to this. Whatever then we end up with on the right will be the answer. Okay, so we do it through elementary row operations, and by design they are done in such a way that we do not gain nor lose answers. So every time we move to the augmented matrix, which represents system of linear equations, and so we're moving on from one system of linear equations to the next. Ideally, you have to make sure that these two equations systems have the exact same solution set. Okay, if they do not, then we are wasting our time. That is ideally the way things should be happening, is that we transition to the next system, and really we can discard the previous one. Not only the computer would appreciate it, that he doesn't have to keep in mind what has happened, but just moving on and on, but it is just logically, you don't have to retrace your steps and find out whether you have gained or lost solutions. Okay, so that in general, it's if you think about algebra of maybe solving equations in general, maybe some high order polynomials, that might be hard, but it can be done with linear equations. So anyway, how we proceed in this fashion. First of all, we ensure that we have 1 over here. That's step number 1. Once we have it, it's called a leading 1. And we use that leading 1 to kill the 2 below it. Okay, ignoring everything else. So that's the beginning of the strategy. We did exactly that over here. If you look at the top, well, actually, we didn't do it. We didn't do it this way. As you can see, we did not turn it into 1, which is the logical step, to keep it more algorithmic once again, to first acquire 1 in the top left position. Okay, then use that 1 to eliminate the entry or entries underneath. Okay, so since we already have 1, I need to eliminate 2 over here. So how? In the same manner as before, which is and multiply and subtract. Okay, so what I'm going to put I will keep the first row, and with the second row, I'll put here twice first row minus second row. Once again, thinking, or rather carrying out operations as if these were vectors. So 1 times 2, you can do it like this, if for convenience, if you feel like it. I multiply the first row by 2, so I'm having 2, 2, 2. I multiply every entry in the first row by 2, so I end up with 2, 2, 2, and then I subtract 2, 2, 2. So what's the result? 0, 0, 0. Okay, at that point, we cannot make it any simpler than that. So that is our answer, even though this is not identity. Okay. However, at this point, we really cannot do anything else. We're supposed to simply write the answer. Okay, based on this analysis, there is no further simplification of the system or of the augmented matrix. So you have to just write the answer, and the answer is really simple. If you go back to the equation, x plus y is equal to 1. So how do you? The idea is usually to express the answer in terms of a parameter or parameters. So when there are infinitely many solutions, parameterize them. Well, what does it mean? It means that you introduce an extra parameter, and then the 2 unknowns, x and y, will be expressed directly in terms of. It's really not complicated. Usually, you pick one of the variables as the parameter. So x equal t, y equal 1 minus t. Okay, so the point is that you can find all the answers not by solving the equation. I mean, you end up with one equation. Okay, so you cannot really use it to find x and y. I mean, you could, but just the way how you do it, that's how you do it. you don't want to solve this equation all the time as you want to produce more and more solutions, but rather you have some kind of parameter which you now plug in value of, and you automatically getting x's and y's. Okay, so then t is the parameter for each of its values. There is a solution. xy. Okay, so that's the idea. And as I mentioned before, it is quite likely that you're going to end up with this kind of answer rather than with the answer that we have, one single number. So whenever the number of variables in the equations is mismatched, that is you are likely to end up this way and not some other way. So you have infinitely many solutions, and then you parameterize in that fashion. And let's also use what we have learned previously to see what we are looking at. We're looking at the same thing. So these two things is the same thing. What is it? What does it represent? What? On the xy plane?
T equals x?
Yeah, I chose t equals x. What I mean is the solution set. What is the solution? The solution set is all pairs xy that satisfy the equation, and they form what geometric figure? A line, yes. So this is a line. This is a line. Both of them are lines, except the first one is the implicit formula. So this is the implicit formula for the line, and this one is parametric, that we have looked at before, but we saw it in the more in a vector form. So let me write it out. So if I just put it in the vector equation, so it will be xy is equal to t1 minus t. Okay, and I can now use I can break it into a standard formula for the line. Remember, what the standard formula for the line is: a point and a direction vector. So what is the point and what is the direction vector? I want to break this, what I have there on the right, into two terms. Remember,
One the point.
what's the point?
One.
You need two numbers.
1 and 2.
Well, let me put it this way. Point, and this is direction. Give me either one or the other.
Direction is 1 and 1 over t minus 1.
No, t has already been factored out. So these two will be just numbers. What?
1 and negative 1.
1 and negative 1, right.
And then the other one, it's 0 and 1.
0 and 1. Okay. So we're getting something that we've seen before, an indirect formula for rather, what's the name of it? It was not point slope formula, but even though you can say point slope formula, point direction vector formula. You can see it right here. Okay, so that is a typical situation when you have infinitely many solutions, but only one. When it is a line, then you're going to end up with such an equation. You can in high dimensions you might end up with a plane or high dimensional spaces, and then you have to parameterize them as well. But before we do that and move on to high dimensions, there is another possibility, and that is let's see. If I take the same equation and change that last entry to 1, so x plus y is equal to 1. 2x plus 2y is equal to 1 as well. So I only change the one entry. So the last entry was 2, right? And now it is 1. Okay, so but then once again, as I mentioned, we do not look at the free terms. The last column is ignored. In fact, all the columns are ignored when you carry out the first step. So then the row operation will be exactly the same. I'm gonna take my to eliminate 2. So I'm using 1 to eliminate to kill 2. Okay, so same way, I keep the first row, so it's 1, 1, 1, and I have I put here twice R1 minus R2, so it will be 0, 0, 1. Okay, so once again, that part is the same. So once again, it's not the identity matrix. Just happens to be, what's the answer?
X and Y are 0.
No. Let's go back. X plus y is equal to 1. I guess I skipped very quickly over this issue when I solved the problem here. I dropped the last row. The second equation is still here. It is 0x plus 0y is equal to 0. Okay, so since it's simply 0 equal to 0, this is the second line, is 0 equal to 0, so it's useless. And that's why we ended up with a single equation, and then we represented it parametrically. But this time it's not the case anymore. We're looking at x plus y equal to 1. The second equation is 0x plus 0y is equal to 1. In other words, the last equation is 0 equal to 1. So, what? What's the answer? No solution. No solution. So when there is the two equations are mutually contradictory. Okay, so we only discovered that through this, well, we could have discovered otherwise, but we only carried out, only after we have carried out the that elementary row operation, we saw that the second equation gave us 0 equal to 1. So that certainly is a condition. It is a condition. Both of the conditions have to be satisfied. Either of the two equations is a condition. So if one of the equations is impossible, then the second one doesn't matter, and so there are no xy satisfying that solution. So the answer then is no solution. We're done. So that's the answer. Let me circle the answer. So this is one answer here, and this is the answer. Okay, the answer, you're certainly saying that it is a line is helpful. Well, let's say line, part of the answer. So the answer is a line, and this is how it is represented parametrically. Okay, in the previous example from last time, my answer is this. This is my answer. Okay, so it's a single point. You can express it as a vector. You can express it as x and y. Doesn't matter. It just depends on the circumstances. But these are we have covered all the three possibilities for 2x2 matrices, and that is one solution, infinitely many solutions, a line specifically, or it is none, no solution. Okay, so only three possibilities, very, very specific, line, point, nothing. Okay, but once we go to high dimensions, then things become more complicated. Okay, so let me point out, so let me go backwards. Let's go to high dimensions, and rather than thinking in terms of elementary row operations, let's think about what we can possibly end up with, and just maybe a couple of examples. So if you look at the resulting matrices, there are two main possibilities. They were 2 by 2. We ended up with so start A, B. Remember that is our augmented matrix, and through elementary row operations we have arrived to on our first occasion A, I don't know, C. With C the answer. Or on the second occasion we arrived to what was it? 1, 1, 0, 0. C. Okay, so we really concentrate on this part. So if when it is the identity matrix, let me erase this to be able to match it. So 1, 1, 1, 0, 0, 1. Okay, that's the identity matrix, and the answer is 1. And the two other possibilities, none or all or none. It is 1, 1, 0, 0. This one might vary. It's not necessarily 1, but we certainly can ensure that one of the variables is 1. Hold on. Can you have? Right. So as you can see, that star that we were able to eliminate in case number 1, we were able to eliminate it. But in the once it just happens that that the second entry in the second row is 0, then we cannot use that entry to eliminate that star. That unknown number, and that's why we end up with what we end up with, the kind of not identity matrix. But now what in general we can end up with is this. Well, first of all, the row echelon form. Of the matrix. So let me just draw it. So it's easy to show than to explain, to write it. But we'll first let's explain. So it is like a staircase. Like this. A staircase. Okay. Okay. These are all zeros. And there are ones in the beginning of each row. Okay. So whatever the rest is unspecified. So I could put a star here. So you have a staircase made of zeros. Okay, so it means that you always go down one step at a time, one step at a time, one stair step at a time. Okay, and in the beginning, at the top of each stair, there is a 1. So these are called leading ones. So as you can see, you have at the bottom, you can have a bunch of 0 rows. So rows entirely made of zeros. I am ignoring the last column once again. As you can see, there is no right column here. So that's one requirement. So if you have a 0 row, we don't throw it out. We just put it at the bottom. Okay, so and we really cannot do anything with it unless it is like 0 is equal to 1, which is what we just had. So then we know that there is no answer. But with the rest we can do some business, and so assuming that we probably wouldn't have to do anything unless all of these are also zeros. We have to stop. So if there is a row which is all made of zeros except for the entry in the last column is not 0, we know we're going to end up with 0 equal to not 0, and so that's a contradiction. So the assumption then becomes that in the last column, that one that follows that vertical line, you have to have all of them zeros. Otherwise, you're done. So if not all are zeros, no solution. Okay, if, however, all of these entries are 0, so literally a bunch of totally 0 rows at the bottom, then you can proceed, and you can throw them out, right? 0 equal to 0, it is useless. We just put it there for convenience. and then now what? Now you can imagine what's happening here is, well, first of all, I want you to see that this is that the identity matrix satisfies these properties. So the identity matrix looks like this, like this. Okay, so and with these it has one in every row and every column. So that's what's so special about the identity matrix. But it is possible that you could have over here non-zero entries, and there might be missing. So you don't go one step at a time. It is a very uneven staircase. That's what you might end up with. Okay, as an example, say. Well, x1 plus x2 plus x3 plus x4 is equal to 1, okay? And then that's this first equation. The second equation, say x3 plus x4 is equal to 2. Okay, you might end up with this. So as you can see, x2 is out. It doesn't have any counterpart below it, which means that, think about it, can I eliminate x2 from the first equation? I cannot. Right, because you cannot pair it up with anything to eliminate it. However, I could eliminate x3 from the first equation. Okay, so we will. The idea is to have as many zeros as possible, and we using these are, by the way, leading ones. This is the leading one, and this is the leading one. The rest are not. So x2 is out. We cannot do anything with it, but we could eliminate this one. So as before, we have leading ones, and we eliminate the entries above it, below it first, and then above them. Okay. However, that's the half of the story. If we go all the way back to this problem, as you can see, we had reached row echelon form right here. This is row echelon form. Right. 3, 4, 0, 1. It is a staircase, and well, it's not a row echelon form. Technically, I need to have a 1 over here, so I didn't quite do it the right way, but it is still workable. Okay, so so that's halfway, but it is pretty good. If you look at that equation that I pointed out here. If we were not to continue the way we did, what could we do? We already know x2. x2 is negative 3/17. So I could have just went on and substituted x1 into the second equation and find x1. Substitute x2 into the first equation to get it is x and y. The name is different. So I could find y from the second equation, right, and then use it to substitute into the first, and then I'm done. So that's one way to do it, but it is kind of we abandoning the idea of dealing with data only and do algorithmically all the way through. So then we proceeded in a different fashion. We proceeded this way, and the only thing that we have accomplished is this 0 over here. Okay, so in other words, we will not only below every leading one you have to have zeros, but also above. So that creates the next stage is called the reduced row echelon form. And reduction is this. So I'll take this thing, and I will just add more zeros in order to explain that. Okay, so like I said, let me just add it. This is what I want to have. So these leading ones correspond to, how should I put it, dependent dependent variables, and the rest will be independent parameters. Okay, so the rest of them are still might be non-zero. Okay, so as you can see, if there is a leading 1, that variable does not appear in any other equation. So there will be a leading 1 per leading variable per equation. So leading 1 per row or per equation. Okay, so then as you can see, these elements are, well, these are the elements are the good ones, these, and then there are more different kind. These are different kind. Okay. So that is just geometrically. I want you to see have that picture in mind. But let me show you what can actually happen through elementary row operations. This is what, as an example, we might arrive to. Say x1, x2, x3. I'll have an equation followed by the augmented matrix. So as you can see, it has been already simplified significantly. And I will demonstrate in a minute that this is indeed a reduced row echelon form. So here it is. I'm putting this in an augmented matrix. So I'll have 1, 0, 0, 2, 0, 1, 0, 1, and 0, 0, 1, and 2. 1, 0, 2. Okay, so once again, I'm omitting the part that we still to be discussed, what the elementary operations might be, and how to choose at every point what to do. But suppose we have done that already, and we arrive to a reduced row echelon form. Okay, so observe that let's confirm that I have what I promised we should, and that is a staircase. This is the staircase to begin with. I have the leading ones. Okay, as you can see above and below leading ones, I have nothing but zeros, and the rest I have no control over. Okay, so let's so yeah, in this one too. So you can see a staircase below. It's always a staircase. So the staircase is made of zeros with a leading 1 standing on each of the stairs. But then what? Also, so that well, actually, probably the way it has happened is the opposite of what I drew, but rather like this: row operations. I have arrived to this augmented matrix, and then I'm done with augmented matrix. I want now to write the answer. So I go back to equations, and I want to write the answer in the form of in the parametric form, just the way we did a minute ago with the with that line. Okay, so do you see what's going to happen now? Well, let me try to show you. So x1 is equal to 1 minus 2x4. x2 is equal to 0 minus x4. x3 is equal to 2 minus 2x4. So does it start to resemble something? Parametric of a parametric equation of a straight line again. Well, I skipped x4. That was a mistake. Well, that's fine. This is what I'm going to do. I'm going to now name x4 that a parameter. So there will be then x4 is equal to t. Or let me move it off. I'll do like this. So I'm choosing x4 because it does not have a leading 1 against it. It will be the everybody depends on. Okay, so x4 1 is equal to 1 minus 2t, x2 is equal to 0 minus t, x3 is equal to 2 minus 2t. Okay, plus. Okay, so x4 is our variable, so that's what the last equation indicates. Okay, so what remains is just to put that equation into appropriate form. Let's put it in the appropriate form. The last system of equations, what is it?
There's one vector that's 1, 0, 2, 0.
Yeah. Okay, so, yeah. Oops.
Then you do plus t times another vector.
Yeah.
Negative 2, negative 1, negative 2, 1.
Okay, and this is my solution. What I have on the left is my solution, and it is expressed parametrically in terms of these two vectors. So solution for each t. Okay, so that's why it is for each t. Any real t will give me a solution. So this is then the answer. And once again, a part of the answer you probably make sense is to say this is a line. However, you can so a line, and it just happens to be a line, but in a line in our form, a four variable, so it is a line in the four-dimensional space. Okay, so however, that is certainly not necessarily the case. So let's remember that we already discussed that early on, what other possibilities you might have in high-dimensional spaces. So in two-dimensional spaces, once again, it is a point, a line, and nothing. In four-dimensional space, as an example, all lower dimensional spaces are possible. So it will be point, line, plane, or three-dimensional space, or nothing. Okay, so let me make up an example from this which produces a plane. How do I produce a plane? I will produce a plane from pretty much the same data, but I will end up with, rather than an equation with one parameter, that's what a line is. It has one parameter. I want to have two parameters. That will create two independent parameters, and that would create a plane. We will connect later to the equation for the plane that we discussed previously. But that's the idea. You realize that line has 1 degree of freedom, one parameter, two parameters, and we will make a plane. So just to see it, let me take this data and tweak it. So how about I'll make x3 to be well, that doesn't really matter. Let me make it up. x1, I'm skipping x2, plus x3 plus x4 is equal to, say, 1. x2 plus 2x3 plus x4 is equal to 2. How about this system? Okay, two equations, four unknowns. And it comes from the augmented matrix of this 1, 0, 1, 1, 1, 0, 1, 2, 1, 2. Okay, so once again, how we got it, we will talk about later. Let's just identify what the answer is. And remember, we will take for each of the non-leading variables, so these are the leading ones, and they will be depend on the other two. So we will introduce t and s. These two variables, x3 and x4, will be the parameters. So this is, let me just write out the answer. I'll have x1 equal to 1 minus t minus s. x2 is equal to 2 minus 2t minus 2s. Okay, and then don't forget the other three variables. X is equal to t, x4 is equal to s. So that is component-wise written up what we already have, what you had before, except as you can see, two variables. So let me quickly just write the vector form of this thing. So x1, x2, x3, x4, that is my vector, is equal to what is the point? Yeah, what is the point?
I don't understand how you're getting the points other than...
The point is that does not have a parameter there. So a parameter plus point plus look at what happened over here. 0, 1, 2, 0, 1, 0, 2, 0 over here, right? And it is simply the terms that have no corresponding t's. Okay? So, and then t indicates in the direction how far we go in that particular direction. So in other words, 1, 2, 0, 0, right?
Okay.
And then I have a t as a parameter, and then I have a s as a parameter. Okay, so what's the first vector?
1, 2, 1.
Negative 1, negative 2, 1, 0. And for the second one, negative 1, negative 2, 0, 1. Okay? So we'll talk about this next time, but this is a plane.